here we will use our newly found boundary conditions on, we'll start with a TE wave hitting a dielectric interface. So let's now draw it in painstaking detail. So here's the interface. Down here we have, say, glass. Doesn't matter for right now. Down here's the dielectric. Up here we're just in vacuum. And in optics, air is basically vacuum. Air, the density of air is so low that you can pretty much treat it as vacuum or an empty medium. Okay, so there's the normal and the incident k vector looks like that, ki, and the reflected k vector like that, and the transmitted k vector like that. And we know our angles. This is theta I. This also is theta I, right? The angle of incidence equals the angle of reflection. And this is theta t. But what we care about is the field. So we're going to use our boundary conditions on the field. So we need to think kind of carefully about the field. Really, we care about the electromagnetic fields right here, right where it hits the surface. I'm going to draw them a little farther out just so you can see them. So when I draw the fields here, you can assume what I mean is right at the interface. I just don't want to draw them all on top of each other. So if this is TE, that means the electric field is transverse to the plane of incidence, so the electric field is like this. So I'm going to draw the electric field with a single vector like that, sticking out of the board. So there is the electric field, and you know that this is a plane wave, so that represents an E field that's going in and out, pointing out and in, out and in. But at this moment in time, at the interface, the E field is pointing out this way. So we can think about what does that mean the B field is doing? Well, we've studied plane waves, so we know that E cross B is the direction of K, so if E is like this, that means the B field is sticking like that. It's pointing down to the right. So this at the moment we'll call EI, and this we'll call BI, a vector. Okay? And when it reflects, we will assume it's going to reflect at the same direction of the E field. So ER is going to stick out. And that doesn't mean that it will. Maybe it'll flip, but if it does, R will come out, the little r would come out negative. The reflection coefficient, if the reflection coefficient comes out negative, that tells us that it flipped. I'm going to set it up assuming that that doesn't happen. But I'm not saying it can't happen, just the way I'm setting it up is assuming that it's the same direction. If it goes the other way, we'll let the reflection coefficient tell us that. Let's see, so if ER is that way, we got to figure out what the BR is. So if it's going this way, then the BR must be pointing down, but now at this angle, because it has to be, these three have to be normal to each other, E, B, and K. All right, and then the same thing for ET. We're going to assume it sticks out like that. ET sticks out, and if ET is like that, then B must be like this. BT. There we go. So that is all that's happening at this little exciting place right here. So let's look at our boundary conditions. One is that the tangential component of the outside of the E field is the same as the tangential component of the inside of the E field, and that's simply saying that EI plus ER equals ET. That's about it. We can write them in one dimension. In this case, I didn't really use vector notation because we're really just talking about the direction tangential to the plane, and we're talking for a TE wave, everything is tangential to the plane of incidence, and we're talking about the plane of the surface, so that essentially turns it into a one-dimensional problem. So I'm not going to write tons of vector notation up there. The other one is Ampere-Maxwell told us that the B field will also be continuous across the boundary, so the tangential component of the B field. So we're going to figure out what that is. So here This is pointing down and to the left, so we know it actually, the B field has a component like that and has a component like that. So there's the tangential component there. This one has a component down and a component like that. That's the tangential one there, so I'll erase these that are not tangential. And then the B field here also, you could write it as have a component like that and a component like that. So we've got to figure out the tangential components of the B field. So let's see, so we have BI this way. If this is theta I, then actually, believe it or not, if that's theta I, then that is also theta I. Because if that's theta I, that's theta I, and then if you take this 90-degree thing and turn it, it turns theta I. So you can find it in there. Go do your geometry. Well, if that's theta I, then the tangential component is just the cosine theta I times BI. Okay? So it's BI, the incident B field, times the cosine of theta I. And we're going to say this way is positive. Okay, that's another thing, is we're now going to use inspection to make everything positive or negative. If we try to rely on it working out mathematically, then we've got to keep up with the sign of these angles, and it's all complicated. It's better just to say the angles are all magnitudes. It's just angular magnitudes. We're not keeping up with, we're not calling this plus and this minus. It's just the angle, and we will assign the directions by inspection. And if we get a direction wrong, like this E field, the number will come out negative and it'll fix itself. Okay? So we've made the tangential B components positive that way. This one, theta I here, ends up being theta I there. The cosine, it's that way, but we're going to call it negative because it points the other way. Minus BR cosine theta I. And those two have to be equal to this one. All right, so on this side, this one we can see points in what we're calling the positive direction, and ultimately it's just this theta t is this theta t, so it's cosine theta t. So it's the transmitted B amplitude cosine theta t. And again, no vectors, because now it's essentially one-dimensional problem. The E fields are this way, the B fields are this way. Okay. So we have two equations. We have a lot of unknowns. We know the incident fields, BI and EI, but we don't know the reflected fields. We know the angles, because we know the laws of reflection and Snell's law, but we need ER, ET, BR, and BT. But we know one more thing. We know the relationship between these two, and these two. We know that you can replace a B field amplitude of a plane wave with the E field over C. Remember the relationship in a plane wave, the E field is C times the B field magnitude. So so we can then take this equation and rewrite it again as BI over C, as EI over C, okay. Cosine theta I, minus ER over C, cosine theta I, equals ET, and now that one's not over C, right? Because here we were kind of in vacuum, where we said in air where you're practically in vacuum, the light goes at the speed of light, C. Here, it goes a little bit slower. It goes at C over 1.5. Right? So in this case, the bottom would be C over N. But C over N means put the N up top. Right? So it looks like that. Then you can cancel the C's. Now we have two equations, two unknowns. Right? All we need to know is ER and ET. So next we'll solve for that. Of course, I knew something was missing here. Right? So a very trivial problem. I forgot to write cosine theta t. So there you go. All done.